fourth seminar of the Italian Reproducibility Network. First, let me thank you, the Italian Psychological Association, Associazione Italiana di Psicologia, AIP, for supporting this seminar cycle. If you want to support us and to stay updated with all of our initiatives and other kind of communication, please join the Italian Reproducibility Network by becoming a member of our network, or if you prefer, you can also subscribe to our mailing list, and you can be updated with all our initiatives. Another way you can support our activities and stay updated with us is to subscribe to our YouTube channel, where all the, for example, all the seminars that we held last year and this year were uploaded, so you can see on our YouTube channel. And also, I would like to remind you that this month we will hold the next ITRN in-person meeting in Rome, and thank you to the University La Sapienza for hosting us. And this event will take place on the 24th of February. Now, I would like to provide you some indication about the Q&A session that will follow the presentation of our today's speakers. You can indicate that you want to ask a question by writing the word question between square brackets into the chat, and we will give you the floor. So you can ask your question out loud. Or if you wish, you can write your question in English or either in Italian, and we will read it out loud and translate it as needed. And also, if you are a PhD student, please signal it to us, and we will give you priority to your questions. Now, let me introduce our today's speakers. Eric Jan Wagenmakers, who is going to take a talk about best practices and transparency in statistics. We are very happy and grateful to have Eric Jan here. And Eric Jan is a professor at the Psychological Method Unit at the University of Amsterdam. His main research interests include Bayesian inference, models of decision-making, and philosophy of science. He has been a staunch advocate of Bayesian inference and open science procedures, such as pre-registration, multi-analyst projects, and scientific transparency in general. Together with his collaborators, he has initiated and coordinated the development of JASP, an open source software program with an intuitive graphical user interface that offer both classical frequentist and Bayesian inference methods. So, Eric, thank you very much for being here, and welcome. The floor is yours.
Thank you very much. It's great to be able to give this presentation. It would have been even better to be in Italy, I guess, but this is convenient, I have to say. So let me share my screen. And obviously, I realize that online presentations are a little bit challenging in terms of keeping your attention up. So I'll try to make this as much fun as I possibly can. And I do think it's a lot of fun, actually. So I'm going to talk about transparency in science and statistics, and it kind of combines my recent work and some ideas that I've been having for a while. And I don't think any of this is spectacularly counterintuitive or surprising, but I do think it has profound ramifications. So this is an overview of my talk. I'm going to talk about bias in academia very shortly, and then I'm going to discuss two sources of hidden uncertainty: cherry picking and model myopia. So first, bias in academia. So this is what I consider to be the main dilemma in science in general. So a researcher, Dr. X, has a favorite theory that she has worked on and published about previously. She designs an experiment to test a prediction from her theory. She collects the data. This can take a lot of time and effort. Maybe she does this together with her students, who knows? And importantly, part of her career and the careers of her students ride on the outcome. So then the data need to be analyzed. If the p-value is smaller than 0.05, the experiment is deemed a success. If it's larger than 0.05, it is deemed a failure. So who now is, without any doubt whatsoever, the most biased analyst to analyze these data? Well, clearly it's that same researcher. So this brings to mind a quotation by Richard Feynman, right? One of his most famous quotations: the first principle of science is that you must not fool yourself, and you are the easiest person to fool, right? Because you're human, we all fall prey to these biases, and we should try to inoculate ourselves against them. So what happens is that data are often analyzed with no accountability by the person easiest to fool, often with limited statistical training, who has every incentive imaginable to produce that p-value smaller than 0.05. And if that happens, if that p-value is smaller than 0.05, the result is declared significant, and any further doubt is frowned upon. Right? So as an example, a student once approached me, and she was studying extrasensory perception, right? The idea that before you pick up the phone, you know who is calling, so you can set up an experiment to see whether this is true. And indeed, they found reject the null hypothesis P is smaller than 0.05. So she came to me with this result and said, like, now surely you must believe in extrasensory perception. And I said, of course I don't. And she became angry at me because I violated this implicit social contract. I should no longer doubt the truthfulness of the result because that p-value is smaller than 0.05. So the statistician John Tukey already warned that statistical procedures should not be used for sanctification, for the preservation of conclusions from all criticism, for the granting of an imprimatur. But of course, this is exactly why statistical procedures are used. And Gigerenzer would compare it to a ritual dance to tell the reviewers, you're not allowed to be skeptical about the results anymore. So what do researchers want? They obviously want to discover the truth. But in addition, they want to present compelling data that leave no room for doubt. They want to develop a coherent theoretical framework, and they want to publish papers that make interesting claims. And in general, researchers, as all people, they abhor uncertainty. Right? So there's always the tendency, if you find a result and it's subject to statistical uncertainty, to kind of ignore that uncertainty as soon as you go from the results section to the discussion section. And there's many different ways in which researchers can fool themselves. So one of the most powerful biases is hindsight bias. So this is abundant in sports journalism. So here you see a picture of a Dutch soccer player in 1988 scoring a very important goal. So this was the Dutch team that actually won the European Championship. And they have had a series of great players, right? Rijkaard, Gullit, Van Basten, all the Milan players, essentially. And it was one of the, it's hailed as one of the best teams in Dutch history, but they were so close to being, to exiting in the group stage already, right? This guy, Wim Kieft, had to score a goal in the remaining minutes against Ireland for them to proceed. So hindsight bias is aptly called the knew it all along bias. So another important bias is confirmation bias, where you downplay information that goes against your worldview. Or, that's also confirmation bias, where you actively seek out information that confirms your worldview. So I have a cartoon here. Oh, the cartoon follows later. So this goes back to Francis Bacon. The human understanding, when it has once adopted an opinion, draws all things else to support and agree with it. Right, so this is the cartoon where somebody goes online and said, I've heard the rhetoric from both sides, time to do my own research on the real truth. And then it says, literally the first link that agrees with what you already believe, and then jackpot. Right, so that confirmation bias. Okay, and this is actually, the bias blind spot is actually my favorite bias. I didn't actually know about it until a few years ago, but the bias blind spot is the belief that you are less susceptible to bias than most other people. And this is also one of the most, it's a pervasive bias. So the insight that people are biased and that this distorts their ability to do research goes back to Sir Francis Bacon, who stressed the fallibility of human reasoning. And he believed that the scientific method should be constructed so that people do not fall prey to those biases. But back then, you know, a few biases were known. I already cited Bacon once, but now if you go online, this is a poster with, I believe, 166 different kind of biases that people fall prey to. So if you see this, it's a wonder that anything gets done in science. And of course, we do make great progress in science, but things can be improved. And one way to improve them and to fight our biases is with blinded analyses. So this has been proposed by McCoon and Perlmutter. So Perlmutter is actually an astrophysicist, and they argued that one way to prevent your analyses from being biased is where one person collects the data and then salts the data, pollutes the data, shuffles labels, does something to the data, and then passes it on to a data analyst. So the data analyst knows this, that the data have been contaminated and cannot search for significance. But if you do it well, the analyst can still make responsible statistical decisions. And once those decisions have been made, once the analysis plan is there, then that plan is executed, the data are unblinded, and that's the result, and no more tinkering is allowed. So that's a really interesting method. The common method that people now start to adopt is pre-registration of analysis plans, with something that they've been done in medicine for quite some time now, where you document in advance what analyses you will carry out. And the purpose of this is simply to separate what was pre-planned from what was data-inspired or post-hoc. So you can still do any kind of analysis you want. You should just be honest that this was inspired by the data and you hadn't thought of it before. So both of these measures are kind of what you can call a Ulysses contract, right? Where you anticipate being tempted, you anticipate that you will succumb to bias. And when you realize this, you take measures, advanced measures, to prevent you from falling prey to temptation. And this is, of course, exactly what Ulysses did when he wanted to hear the call of the sirens. He tied himself to the mast, he put wax in the ears of the rowers, and this way he was able to hear the call of the sirens without being shipwrecked, right? So here you see a researcher and the sirens are singing. The story is just so much clearer if you just omit that second experiment. But because the researcher had pre-registered that experiment or was collaborating with other people and did blinded analysis, that's not no longer a valid option for the researcher. Or at least the researcher is now very much attended to the fact that he's about to make a very biased decision. So whenever I say this, people in the audience, they nod. And I've presented this, for instance, to cognitive psychologists, and they generally think that only social psychologists have this problem and they're fine. And so I read to them this editorial from Psychological Science from Steve Lindsay, who said, this is a few years ago, personally, I aim never again to submit for publication a report of a study that was not pre-registered. Exploratory work has great and essential value, but is typically not appropriate for publication. Now, if one of the editors of the main journal in the field says these things, right, it kind of hits home. Maybe we should start to pay attention to this technique. Okay. So now on to two sources of hidden uncertainty in modeling, cherry picking and model myopia. And I particularly think that model myopia is one of the more interesting ones because it has been ignored for such a long time. but I'll get to that after I deal with cherry picking. Okay, so cherry picking is where you test many different things, or you look at many different things, and then you select the ones you like, the ones that turn out well, and you do not mention that you looked at many other things too. And model myopia is where you test and report the outcome of only a single model. And that can seem perfectly reasonable, but it does mean that if somebody else would analyze the data, they might use a different model, they may draw a different conclusion. So without addressing this issue, you have no clue how robust your conclusion really is. Okay, so on the statistics of cherry picking. So some background here, you see a picture of Adriaan de Groot, the founder of my department. And he made a conceptual distinction, as some people did before him, between research that's hypothesis generating or abductive and hypothesis testing. So the key argument is that when the data inspire a hypothesis, you cannot use those same data that test the hypothesis. So schematically, we start with old knowledge and old data. We speculate and explore. This is the abductive process. We arrive at a new hypothesis. And that from that new hypothesis, we deduce predictions. And then we do an experiment. We get data from the experiment. We do a statistical analysis. We evaluate the outcome. We accumulate knowledge. And this is one cycle of learning that we can then continue to do. So over to the right, we have the creative context of discovery, where you think of new hypotheses. This is a process that's not well understood. And we have the statistical context of justification. So it's really important to keep these two contexts apart, because there's a temptation, and the temptation is not to do a new experiment, but to take a shortcut in this empirical cycle, where you have the data, they inspire a hypothesis, from the hypothesis follows a prediction, and that prediction is tested on exactly the same data that gave rise to the hypothesis. No wonder that the hypothesis comes out looking really well, and it looks like the hypothesis is supported by the data. But it's almost impossible for it to be any other way. So this is when you're fooling yourself. And this is what the picture looks like when you have it drawn by somebody who knows what they're doing. Okay, so this is what Richard Feynman had to say about it. And Feynman, a famous physicist, right? He was actually an RA for a psychologist when he was a student. And he describes here what his experiment was. So back in the day, psychologists usually would study rats and how rats learn to navigate a maze. So Feynman says, and it's a general principle of psychologists that in these tests, they arrange it so that the odds that the thing that happens by chance is small. In fact, less than 1 in 20. That's the p-value, right? 0.05. And then his boss, ran to me and he said, calculate the probability for me that the rats should alternate their paths so that I can see if the probability is less than 1 in 20. I said, it probably is less than 1 in 20, but it doesn't count. He said, why? I said, because it doesn't make sense to calculate after the event. You see, you found the peculiarity, and so you selected the peculiar case. The data inspired the hypothesis. If he wants to test this hypothesis, then he cannot do it from the same data that gave him the clue. He must do another experiment all over again and then see if they alternate. He did, and it didn't work. So this is also described in 2 books by Ben Goldacre, Bad Science and Bad Pharma. And that's obviously, Ben Goldacre is a medical doctor, so this is very much targeted towards medicine, but that also underscores the practical relevance of what we're talking about. So now a more statistical perspective on this problem. So if you're cherry picking, if you approach the data with the attitude, let us see what we can find, then effectively, you're creating a multiple comparisons problem with the number of comparisons unknown. So a frequentist will argue that this brings our type 1 error rate to 1. So even in pure noise, if there's absolutely nothing there, you're bound to find some regularity. So the problem here is that sometimes people are just, sometimes people are really data dredging. They have no hypothesis a priori. They just let themselves be completely inspired. And sometimes, you know, there's only a few decisions that are data inspired, but without this being documented, it's very unclear what has actually happened. So what are the relevant multiple comparisons when we talk about that multiple comparisons problem? Well, first, there's the ones that you can clearly see. They're in the manuscript. Those are the tests that are conducted in publications, right? And if you read most publications on empirical findings, you see that they report many different tests and almost never correct for multiple comparisons. But then there's also the ones that didn't make it to the manuscript, but that the researcher who presented the findings did execute in, say, R or SPSS or JASP. Those are relevant for your statistical evaluation too. But also, there are the tests that you executed by eye. You look at the data, you see a difference somewhere, and then you test that difference, right? Implicitly, you were testing, you know, very many other hypotheses by eye and rejected those. And then you also have tests that could have been executed had the data come out differently. And you may argue, why would we care about that? Because these are the data we have. Why would we care about data that could have been, but were not? Well, you're right. But if you strongly believe that, then you're a Bayesian. If you believe that this should matter, then you're a frequentist. But the main problem here is that usually we only know the first category of multiple comparisons. Okay. So we're about halfway. So it's time for a short commercial break. So I'm not going to talk about JASP, but I will say that if you want to learn more about it, you can go to jaspstats.org. And JASP is an open source statistics program. It does classical analysis. It does Bayesian analysis as well. And we really try to implement methods in a very clear way, useful for students, but also state of the art. And we believe that we're already at a stage where you can basically ditch your SPSS license and adopt JASP instead, and your students will thank you. We have a large number of people who work on the program. This is not up to date, but it gives you an idea of how many people are contributing. And this is a screenshot. It happens to be a Bayesian independent samples t-test, and you can see here the idea is that you drag and drop variables in boxes the way you do with SPSS, and then in our GUI, immediately you get output on the right-hand side. And if you want more output or different output, you tick and untick boxes, and the output dynamically changes. At the moment, there's 259 universities from 63 different countries where teachers have let us know that they're using JASP in their courses. So this is an underestimate of how many teachers are actually using it, because this is only what teachers have told us. I've zoomed in here on Italy, and you know, it's okay-ish, but I think we can do a lot better. And in fact, JASP is available in many different languages, and currently, I think we have Italian. I don't think it's in JASP just yet, but we've made it relatively easy to do translations. So if you want to help with the Italian translation, look up online how you can do this, and there's a program, WebLate, that makes it relatively straightforward to translate the strings. And so once everything is translated, then in the preference menu, you just set it to Italian, and the whole thing is Italian, output, GUI, everything. Okay. Now, we also do annual workshops. And they have gone live since yesterday. So since yesterday, you can actually register for them. They're in July in Amsterdam. I'm not sure what the weather will be like, but I'm guessing it will be better than in Italy, unless you like 40 degrees. Anyway, it might be 40 degrees in Amsterdam as well. I cannot give any guarantees, but I can guarantee that these workshops are educational and fun. So please check them out. If you want to learn more about Bayesian inference, I also would recommend that you read my children's book, Bayesian Thinking for Toddlers. If you Google it, you can find it. It's freely available online. Okay, that was the commercial advertisement. So back to business. Model myopia, perhaps my favorite topic and the one that I spent most time on recently. So, what is model myopia? Well, when you read an academic article, usually the key test is conducted using a single analysis conducted by a single data analyst. But we can wonder, what if data pre-processing choices would have been defensible but slightly different? What if a different model had been used? What if other analysts would have been invited to analyze the data? Would they have drawn the same conclusion? And there lies a large part of the statistical uncertainty, but it's hidden beneath the surface. And so it is, I always thought it was peculiar that when you read statistics journals, they worry about, is the Ewan-Feld correction better, or the Greenhouse-Geyser correction, et cetera, et cetera. But it's rearranging deck chairs on the Titanic. And we do need to rearrange those deck chairs on the Titanic, but we also need to be aware of the iceberg, right? And the iceberg is that whatever analysis you do, if you give your data to a different person, I guarantee you they will do a different analysis, right? With a different outcome. It may support your claim, but perhaps it does not. And we desperately need to know this. So this is work that I did together with Balázs Axel and Alexandra Sarafoglu. So one paper we did on this recently was 7 steps towards more transparency in statistical practice. And what we really wanted to do is we wanted to make the claim that statisticians actually agree on a lot of things, right? Because if you would think like, well, they disagree on even the most fundamental things, right? What is probability? Should we use this particular approach or this other approach? There's a lot of debates among statisticians. And when you read the debates, you could think like, well, they don't agree on many things, but actually they do agree on a lot of things. And what do they agree on? The ethics of their profession. And there are some very good ethical guidelines by the American Statistical Association. And those ethics are basically in line with the Mertonian norms of science. So I will very briefly remind you what those norms are. So the first norm is communalism. So what that means is that the results of science are the property of all scientists. So property rights in science are whittled down to a bare minimum by the rationale of the scientific ethic. And secrecy is the antithesis of this norm. Full and open communication, its enactment. Right, so that's communalism. And then you have universalism. So truth claims are to be subjected to pre-established impersonal criteria. Right? So the acceptance or rejection of claims is not to depend on the personal or social attributes of their protagonist. So just because Gerd Gigerenzer says something, or just because Richard Schifrin says something, should not mean that you accept it as truth. You should be skeptical and critical no matter who makes a claim. The third norm is disinterestedness. And disinterestedness does not mean that you're not interested in what you're doing, but it means that what you say and what you state is not influenced by considerations of personal advantage. So it basically means that you should avoid conflicts of interest. A passion for knowledge, idle curiosity, altruistic concern with the benefits to humanity have been attributed to the scientist. And then the fourth and final norm is organized skepticism. Most institutions demand unqualified faith, but the institution of science makes skepticism a virtue. So I think when you present scientists and statisticians with these norms, almost everybody subscribes to them, right? Because they go to the heart of what it means to be a scientist. But when you take these norms seriously, they have ramifications for statistical practice. So they highlight the need for transparency. They highlight the need to acknowledge uncertainty and the need for openness to alternative interpretations. So that 7 steps paper wanted to change the status quo in ways that all statisticians would support, because the changes follow from the Mertonian norms. So here you see 7 concrete measures that could be taken, and the table indicates to what extent or what specific Mertonian norms they relate to. So we have visualizing data, quantifying inferential uncertainty, assessing data pre-processing choices, reporting multiple models, involving multiple analysts, interpreting results modestly, and sharing data and code. So I won't go over all of them, you just have to read the paper, but I'll go over a few. So visualizing data. You can do it like this. This is a screenshot from JASP, right? This is a rain cloud plot. They are becoming increasingly popular. They should basically show all of the data. And when you look for reasons as to why we should visualize the data, there's, I think, no better illustration than Anscombe's quartet. So Frank Anscombe was a statistician, and he constructed 4 data sets shown in these 4 panels. And he constructed them such that the mean and the variance of X and Y are the same, and the correlation coefficient is also the same. You can see Pearson's R, a measure for the linear relationship between 2 variables, is 0.816 for each 4 data sets, in each of the 4 panels. But only in the top left panel does this actually make sense to report and interpret. The top right panel has a quadratic relationship. The bottom left panel has 1 outlier and is otherwise perfectly linear. And the bottom right, there the result just depends on a single outlier. And in fact, I once reviewed a paper where somebody reported a correlation without showing the scatter plot. I asked for the scatter plot, and I got back the bottom right scenario. Right? So I did not say then that the paper should be rejected, but I did say that that plot should be in the paper, right? So that readers know what the results really are. And if you look online, you will find extensions of this idea where you can actually generate all sorts of data that look completely differently but have the same correlation coefficient, right? And so this is just one example, and the dinosaur you see on top is known as the Anscomosaurus, in honor of Anscombe, right? So if you have a picture of that dinosaur and you try to, look for a correlation, or you try to do a statistical test or whatever, right? Not showing the picture, not being aware that those are the data would be seriously misleading to you and to your readers. Okay, so this is the URL. But if you Google Anscomosaurus, then I'm pretty sure you will land on this page. This is actually, there's some really good statistical work that underlies these plots. Okay, so step 3, assessing data pre-processing choices. So otherwise known as a multiverse analysis, based on a paper by Sarah Stegen, Francis Stirlings, Andrew Gelman, and Wolf van Tamel. So what did they do? They looked at a paper and they noticed that a lot of choices were made on how to pre-process the data, right? And a pipeline of analysis choices. And they basically argued that a lot of different choices could have been made that were also defensible and plausible, right? And obviously, very quickly, this tree of possibilities explodes. So you have very many different pipelines. And for every pipeline, you could then conduct the specific statistical test that the authors conducted. So you see two examples here. So it doesn't matter what the topic is. This is a histogram of p-values that result from all of those different pipelines. So the red one, the red dashed vertical line, that corresponds to the p-value that was actually reported in the manuscript. And the histogram is what you get when you do this with other pipelines. And so you see that in the top panel, there's considerable lack of robustness here. And that would really be a problem, but you usually don't see this at all. And in the bottom panel, I would argue it's still a big problem, but maybe less of a problem, but still a problem. But this is only what happens when you choose different pipelines. But still, you do the very same test that the author did. But obviously, you can do different tests as well with different models. So that's what you get when you involve multiple analysts. So this is argued in this paper. So you see the iceberg picture. We actually gave Nature our iceberg picture, but they have a very good graphical designer, artist, and they wanted to make their own picture. So this is their rendition of that picture. One statistical analysis must not rule them all. And that makes the point that if you want to assess robustness, you need to look at what multiple different analysts conclude from the data, because they will all use different models. So this is one example from a paper that was published a few years ago now, I think. Many analysts, one data set. So here you see the different analytic approaches. I think there were somewhere in between, I think there were something like 24 different teams or so. And they all analyzed the same data set. They all were given the same hypothesis, but they could, choose their own modeling approach. And as you can see from the left-hand side here, every team took a unique approach. There was not a single team who took the same approach, right? We go from mixed model logistic regression to multi-level regression to hierarchical Bayes to negative binomial regression, cross-classified multi-level negative binomial, etc. And then you see the outcome. And so most teams report an effect. If you go, let's just keep things easy and say, like, we're just going to see whether the 95% confidence interval overlaps with 0 or not. Not my favorite measure, but let's just do that. Then you can see here that most teams argued that there is an effect. Doesn't matter what the research question was. Most people argue that there is an effect. But there were some teams that argued that there is no evidence for an effect. And actually, I was part of a team that argued that there was no evidence for an effect. So we actually found, I should tell you something about the context. So this was about soccer players. Thanks for I see I have 5 minutes. That's perfect. So this was about soccer players. And the question was, will soccer players with a darker skin tone have a higher probability of getting a red card? That was the question. And so we found that there were, in our analysis, at some point, we looked at the data. At some point, we found that there were 3 players from, I think, African descent. And basically, those 3 players, every time they were put on the pitch, they immediately kicked somebody and were sent off. They always got red cards, right? So for our analysis, the inclusion of those players mattered a great deal. So we attended the other teams to this, but for their analyses were more robust to either including or not including those outliers. So, but what this shows, and other many analyst approaches have shown similar results, is that often there are substantial changes between one outcome and the other. So that's important to know. So the last one that I want to discuss is interpreting results modestly. So this result was published in the magazine Significance. So what we did is we emailed authors from Nature Human Behavior. And Nature Human Behavior, what they did until this paper was they took the main claim of the paper and put it in the title. And so we emailed the authors and we said, how plausible, how confident were you in this claim before you did your experiment? And how confident are you now after you've done this experiment? So you would hope, if the claim is in the title, that all of them become more confident. Well, these are the results. So you see, indeed, a rare case of scientific consensus. All 31 authors who responded indicated that they were more convinced than before they did the experiment. Right? All these lines go up. The data points after they saw the data are higher than before they saw the data. However, when you look at the plausibility assessment, they had to give a number between 0 and 100. You see that there's still substantial uncertainty that the researchers themselves indicate, right? Some are at 50-50, right? Others are up to 75%, right? But imagine a paper in Nature Human Behavior that says, we are now 75% certain that this particular thing holds, right? That would not be accepted. That would be deemed way too uncertain. So what people write and publish is not what I conclude this tentatively, may not be reflective of their own sense of uncertainty. Okay, so in the interest of time, I will skip step 7, sharing, but I will just say sharing data and code is a good idea. But I think I don't need to do that here. So concluding comments, we sorely need more transparency. We're moving in the right direction, but it's important to keep the momentum going. So I like to compare transparency to mental hygiene. So the scientific equivalent of brushing your teeth, washing your hands after visiting the restroom. So we need a change in culture, right? I have young children. I can tell you, initially, young children do not like to brush their teeth or wash their hands after visiting the restroom. But we all think it's important. And once you're used to doing this, you cannot imagine that you didn't want to do that, right? Sometimes I go to a conference and I forget my toothbrush. I'm not exactly in a state of panic, but it deeply inconveniences me, right? And so I think we should look at the same way at the need for scientific transparency. So I think journals and funders should start demanding that kind of mental hygiene and also rewarding it. And one option could be that journals should prefer papers that conduct a multiverse analysis. And hopefully the American Statistical Association will also encourage more statistical transparency in the future. That's it. Thank you very much.
Thank you, Eric. Yeah, your presentation was really, really insightful and really interesting. And thank you very much for taking it. For taking it. Yeah.
Should I stop the screen share? Or do you want me to leave it on?
If you want, yeah. Now let's start the Q&A session. I have already seen that Carlo has raised his hand. So Carlo, if you want to ask your question, the floor is yours.
You're muted, Carlo.
Yeah, exactly.
Sorry, it was a mistake. I wanted to clap the hands, but there's no option available.
Okay. Does anyone has a question to ask to Eric Jan? Let me see in the chat if someone.
I think that's generally the problem with the topic, right? So it's so simple. It looks so obvious that we should do things this way. It kind of corresponds to how a child thinks that science ought to be conducted, right? But then again, that's totally not the way it works. So
no, exactly, because from your presentation, I learned that the idea of pre-registration dates back in the 18th centuries, 19th century, so 1883. It's kind of right that that idea of the way of doing science in a transparent way didn't get much attention from the scientific community, and I was wondering, why do you think is that?
Yeah, that's very interesting. So I do think that the recent changes that we've seen, right, the reproducibility networks that have, come into being, the fact that data sharing is now more or less expected. We have all these preprints. I think a lot of it is due to the fact that our world has become so small, just because of the internet and email, that, imagine trying to do all these things that we now take for granted in an era, say 30 years ago, right? So I still remember as a student, I had to print out my manuscript 5 times, send it overseas to an editor. The editor would send it out again, right? The paper versions, collect the feedback, write back. So it's a very, very slow process, right?
Yeah, and so the technology.
Yeah, and so data sharing, now it's kind of trivial, right? You go to the Open Science Framework, you do a click, click, click. You still have to think about proper archiving, etc. But technology, the logistics are now so dramatically different from what they were before. So I think the fact that it's now easier is a big part of it. And before, there were isolated cases where people argued for a particular methodology, but it simply didn't catch on. And I think it was too difficult, I think, at the time, too effortful. And now it's feasible. That's at least my take on it. Yeah. I think Frederica has her hand up for a while now.
Yes. Thank you very much, first of all, for the presentation. And okay, let me lower my hand. I have the impression that sometimes, from what you said and from what I observed, sometimes it would be easier if someone collected the data and then it was a different person analyzing it.
Yeah.
But on the other hand, sometimes I feel like it's really, really difficult to analyze data when you are barely aware of what the hypotheses were, the idea were, what kind of data it is.
Yeah, totally. That's absolutely true. Yeah, I know.
How do you find the balance?
Yeah. But sometimes the opposite is actually true. So I was in a project where we collected data and then we wanted to fit a pretty complicated model. And fitting that model was actually going to be painful for us. So what we did is we involved somebody else who was an expert in that modeling technology. And we said, we're going to send you the data. We're going to, shuffle the labels. You are in charge of the modeling, and then we'll look at the result. And that person thought it was a great idea. So that actually made it much easier for us. But I do accept that in general, there could be a challenge in finding knowledgeable analysts. I know that a colleague of mine, Jelte Wiggerts, has argued for a co-pilot system where you only need one other analyst, right? This is basically like when you fly a plane that you have 2 pilots in there, right? One other person who sees the data, who goes over the analyses. So kind of my hope is that at least for results that are, important, that we go to a system which is also done in statistics occasionally, where you have the main paper, and then at the end, there are 2 comments separately from the main paper, but there's 2 or 3 comments by other people, And they could be reviewers or just methodologists with experience in that particular field. And they are allowed to comment on the paper and do a very small reanalysis. So then at least you get an idea. And I think, so when we do this, when we have a data set and we say, are there teams interested in analyzing this and becoming an author? Right? We did this for recently for a project, and I thought, how many teams will we get? In a week, we got over 100. Right? So I think people are really interested in doing this. And for when you're an expert in a particular method, you want to showcase it and you want to apply it, and it doesn't need to take you too much effort. There's always exceptions, of course, and I think it's up to the researchers to clearly explain their hypotheses and what they were doing and what they were after. So I agree it has challenges, but on the other hand, I think, this is clearly something that we should just try out. And then in trying it out, we'll see where the bumps in the road are, and maybe we can smooth those over. Yeah, but it's a good point.
Thank you. Thank you. Okay, I see Laura Anna has raised his hand. If you want to ask your question.
Yeah, hi. Sorry, I don't think my camera works, but thanks a lot for this amazing talk. We learned a lot of stuff. I was wondering, because all of us now are, at least thinking about pre-registration and register reports. And today we learned that there's much more than that, right? And also what you were just discussing with Federica. What's your opinion? Is pre-registration actually good enough? Are you happy if now the entire field does only, let's say, pre-registration, or you think we have to do much more than that?
Yeah, it's interesting. Well, no, I do think we have to do more than that, because pre-registration accomplishes one thing, right? It's a Ulysses contract. So it's really good for people to be aware of, what they were hypothesizing before they saw the data and what is data inspired. So that's great. But you actually run the danger of even increasing model myopia, right? Because you think I'm going to do this analysis because that's the one I pre-registered, and I'm going to look at nothing else because I didn't pre-register it, right? And so, of course, you could pre-register a multiverse analysis. You could pre-register a many analyst effort. It's all possible. But I think we should be consciously aware of the fact that this is also an important aspect of uncertainty. And I would say now, when this is still, kind of a new idea, I would encourage everybody who's working on a research project to see whether you can do, you don't need to do 100 different teams or something, right? But just 2 or 3 different analyses would already be interesting and go well beyond what is usual in the field. In your field, you would probably be the first one to do this multi-analyst effort, even if you have just 2 or 3 other teams reanalyzing your data. So I think that would be methodologically really cool to add at this moment. Maybe in the future everybody will do it and then it will become less cool, but now it's still very uncommon.
Thanks a lot. Very clear.
Okay, I believe that Marco Tullio had raised his hand. Okay, please, Marco.
Hi, thanks for the talk. I was wondering whether there are some instances in which sometimes it is useful that the data analysis is performed by people who are actually carrying on the investigation. For instance, when you develop a scale and you do some factor analysis and try to find which items should be removed, how to interpret the factorial solutions, I think that in that case it might be useful. I mean, to know what are, but
totally.
But also maybe I can also anticipate that a possible response is that this is an instance of an exploratory research endeavor. So maybe in that case you're excused for doing that. Whereas if you want to run a confirmatory factor analysis, for instance, then it should be better to outsource that analysis to to other people, because then you may start wondering, should I use this estimator, this other estimator, and so on. What are your thoughts about that?
Yeah, I think you answered your own question, and I'm in complete agreement there. So I would also say that just to give a little bit of context, if I say, if I make the claims that I made today, there's one group of people that really firmly disagree with them, right? So this is like almost a little bit like the Asterix and Obelix, where the whole of France has been conquered except this little village. And I think most people now are on board with open science and transparency, etc., except mathematical psychologists. And they are my close colleagues, right? I'm a mathematical psychologist by training, and they are violently opposed to almost anything I say. And I think the reason is because most of their work is in the abductive stage, where they're developing models to explain phenomena, right? But they're not really, they don't really have fully specified models that they then want to test empirically, right? That's usually not what they do. They just try to, come up with a good explanation, and then so it's a different, it's a different part of the empirical cycle. And I think when you're in that different part of the empirical cycle, people lose the ability to talk to one another in a productive way.
Okay, thank you very much. Does anyone else want to ask a question? Okay then. So let me say some concluding remarks. So first, I would like to thank you again, Eric Jan, for your presentation. It was really, really interesting and insightful. Thank you very much for being here today. And
thank you. It was my pleasure.
Also, thank you to the audience for being here today and listening to this wonderful presentation. And I would like to remind you that late in this month, we have the next ITRN meeting in Rome, which will be held in person at La Sapienza University on the 24th of February. And about today's seminar for PhD students that need the certificate for for educational purposes, an email certifying your attendance to this seminar will be sent to you within the 7 next days. And the next month's speakers will be Dr. Enrico Glerian, which is going to speak about open issues and data sharing. And finally, I would like to remind you that if you want to support our activities and initiatives and you want to learn more about them, you can either join our network or you can subscribe to our mailing list, and also you can subscribe to our YouTube channel. It's really helpful if many people can support us and what we do. And thank you very much again, and see you in Rome. Bye, Eric. Thank you.
Bye-bye. It was my pleasure. Thanks to everybody for listening so attentively. I know it's difficult through Zoom, so thanks.
It was really easy. You make it really easy.